So in my last science video, I talked about what I called a throwaway term, carbon dating. Now, carbon dating is an actual discipline, although I don't think it's ever actually been reliable. So the term itself is not a throwaway term, but when I call it a throwaway term, what I mean is a lot of people use it inappropriately in the wrong context. So when they use carbon dating, what they really mean is, sorry about the noise, there was some rain earlier and the cars are driving through hitting puddles. What they really mean is radiometric dating. Carbon dating is a form of radiometric dating, but radiometric dating is a broader term. And what they mean a lot of times with the radiometric dating is actually a different form, and that would be dating of rock formations. Now, carbon dating is a form of dating for organic and soft tissue material, and the dating of rock formations is different. So, just to get that out of the way. So when we're talking about the radiometric dating for rock formations, what we're going to talk about is this. It is called parent-daughter element dating. So you would take a pair of elements, like, and the one I'm going to talk about just because it's the one I can always remember, it would be radioactive potassium, which decays into argon. So radioactive potassium has a half-life, and I should have looked it up before I started the video. I did not, but it's several thousands of years. So the theory is that if you had a pound of radioactive potassium, then in so many thousands of years, half of that radioactive potassium would decay and become argon. So in one half-life, you would then have half a pound of radioactive potassium, half a pound of argon. In two half-lives, you would then have a quarter of a pound of radioactive potassium and 3/4 of a pound of argon. In three half-lives, you'd have an eighth of a pound, and so on and so forth. You can extrapolate, do the math. Theoretically, you would never actually run out of radioactive material, but the math would continue to just go on like that. And I'm not going to try to go beyond an eighth because I'm not going to try to do that math in my head. It's been a long day. I'm tired. In any event, here's the problem with the method. Radioactive potassium happens naturally. There has to be no other elements occurring in nature for radioactive potassium to occur when a rock forms. But argon also happens naturally. So you don't have to have radioactive potassium for argon to occur in a rock formation. Now, it does happen at the decay of radioactive potassium, but it also happens on its own. So it's out there floating in the atmosphere without the decay of the parent material. So, in order to accurately date a rock formation, you have to know whether or not there was argon present when the rock formation occurred. So if you're going to accurately date a rock formation that you believe to be billions of years old, the only way to do that is to have been there when the rock formation was formed. To have taken your readings of the radioactive potassium and the argon when the formation occurred. Otherwise, the only thing you can do is assume how much argon was or was not present at the formation now when you're doing your equations to extrapolate how much should be there now. So essentially, you have to take how much argon is present now, subtract how much you believe was present in the beginning, so that you can then determine how much of the present argon was radioactive potassium, so that you can determine how much of the radioactive potassium has decayed, so that you know how much of the half-life has already escaped, has already happened, so that you can then extrapolate how much of the... You understand? So, if your calculations are incorrect, and you assume wrong about how much argon was there in the beginning, that puts your calculations off. And even minor calculations, when you're dealing with thousands of year long half-lives, minor calculation inaccuracies can then become millions and billions of year inaccuracies in the math. Does that start to present a problem? Does that start to tell you that maybe these radiometric dating disciplines based on assumptions might not be nearly as accurate as what they're telling you that they are, and this billions of years old planet could really be thousands of years old, not billions of years, because our math is messed up, because we're doing our math based on assumptions, not based on hard evidence. That's what it tells me, because every single parent-daughter element pair, both of the elements occur naturally. So both of the elements could have been present in the rock formation at the time of formation. So every single set of parent-daughter elements is based on, or could have been there. Every single time that they do one of these calculations, they have to build in assumptions. Every time. There is no way, there's no set of them where the daughter element is entirely dependent on the parent element's decay. There's no single one of them where you have to have the decay of the radioactive material for the daughter element to exist. So at no time can you definitively say the daughter element has to be existent only because the parent element decayed. So we have a definitive set of equations that tell us this rock has to be this old. It does not exist. Every single set of parent-daughter elements both exist in nature naturally. And so you cannot create an equation without an assumption. And even small errors in assumptions become millions of billions of years worth of potential inaccuracies. And the simple fact is, if you're the one dating the rocks and you want them to be older, you just massage the numbers so that they're older. Small tweaks, big differences. And we're humans. We're humans. We're given to making things look the way we want them to look, not the way that they actually are. Just food for thought. So that's radiometric dating for you. Look into it yourself. I'm not asking you to take my word for it. Look into it for yourself. We'll see you on the next one.